The story of the universe begins not with thunder, but with silence. A silence so perfect, it bordered on impossibility. A silence in which every particle was balanced, every corner of space smoothed to an almost featureless calm. It was a canvas, without texture, a stage without motion, holding within it the possibility of all that was to come. Entropy, the law that drives disorder, that ensures decay, collapse, and the long fading into heat death, had not yet spoken. Its voices, the crackle of stars burning out, the collapse of galaxies into black holes, the drifting of heat into emptiness. Yet in that first moment, it remained mute, its rise held back, its story unwritten. And here lies the paradox. If the universe is destined to unravel into chaos, why did it begin so improbably ordered? Why did time's arrow require a beginning so silent, so exact, that no known law of physics can explain its precision? The cosmic microwave background, the first afterglow of creation, reveals not turbulence, but an uncanny smoothness, as if creation itself hesitated before allowing disorder to enter entropy. Is the narrator of the cosmos, the voice that guides every star and every breath toward eventual ruin. But if it must always rise, why did it choose to begin in stillness? Why was the first word not noise, but silence? The 19th century was an age of fire and iron. Across Europe, the hiss of steam and the clatter of engines echoed through cities and valleys. Coal burned without rest, feeding furnaces and locomotives, the pulse of an industrial world awakening. Hidden within this age of progress lay a mystery. Every machine, however powerful, wasted something. Heat poured out into the air, lost and unrecoverable. Engineers spoke of inefficiency, but the deeper truth was not merely mechanical, it was fundamental. Nature itself seemed to bleed energy into silence in 1850. A German physicist, Rudolf Clausius, set himself to the problem. He studied heat not as a craftsman, but as a lawgiver. Why did heat always flow from hot to cold? Why could no engine ever convert fire into motion without loss? From these questions, Clausius carved a principle that would haunt all of physics. He gave it a name taken from the Greek word for transformation: entropy. Entropy was not heat itself, but the measure of its dispersal, a quantity that told of how energy spread from order into disorder. Wherever fire burned, wherever steam drove pistons, entropy grew. Clausius declared with stern precision, "The entropy of the universe tends to a maximum." It was a sentence at once simple and terrifying, for it implied that all fire, all heat, all life would one day thin into cold stillness. Entropy was not merely a property of engines, it was the destiny of the cosmos. Yet Clausius had only uncovered the outline of the shadow. The deeper explanation required a mind attuned to the secret movements of atoms. That mind belonged to Ludwig Boltzmann in Vienna. Boltzmann envisioned the hidden swarm. Every gas, every liquid, every solid composed of countless particles colliding in endless motion. Heat was nothing more than their frantic dance. And entropy was the language of probability written across their motions. Boltzmann saw that order was rare and fragile, while disorder was natural and overwhelming. A gas pressed into one corner of a box was improbable, but once released it would spread. Not because the molecules knew a law, but because there were immeasurably more ways to be spread than to be confined. Entropy was the mathematics of this truth. It measured not just energy, but the number of possible arrangements of the microscopic world. Boltzmann carved his law into stone on his own tomb: S equals K log W. Entropy equals the constant multiplied by the logarithm of the number of states. It was a simple equation and, yet it bound probability to destiny. The cosmos itself would always drift toward the greater multitude of possibilities, toward disorder, toward silence. But here, the first whisper of unease entered. For Newton's laws of motion were time-symmetric. They worked equally well backward as forward. If every molecule could retrace its steps, why did they never do so? Why did entropy always rise? Why did time move in only one direction? This was the riddle of the arrow of time, born not in astronomy, nor in philosophy, but in the smoky air of factories and the chalkboards of physicists. Time itself seemed chained to entropy. Each tick forward, each memory, each life depended on the rise of disorder. Boltzmann struggled with this paradox. He argued that the universe might simply be a fluctuation, that perhaps on cosmic scales it was almost always in chaos, but by chance for a brief interval it had dipped into order, and from that order life and time had emerged. A daring thought, yet unsettling, for if true, then memory. The stars even thought itself were nothing but improbable ripples, soon to vanish. His contemporaries resisted. They could not accept that the fate of time was hidden in statistical chance, nor could they accept that the destiny of the universe was to fade into heat death. The debate wore on, leaving Boltzmann in despair until his life ended tragically. Yet his ideas endured, for hidden within his mathematics lay a key. Entropy was not merely about steam engines or molecules. It was about the very structure of reality, the very reason time flowed. From Clausius's careful formulations to Boltzmann's statistical vision, entropy had revealed itself as a law deeper than mechanics, a whisper from the foundations of the universe that all things tend toward dispersal, that order once born will always erode, that silence awaits, and so in the age of steam, amid pistons and smoke, humanity first glimpsed a truth that stretched to the birth and death of the cosmos. Entropy was not the invention of the 19th century. It was the fate written into the universe itself. But it was there in that century that humans first gave it a name and heard its voice. The first whisper of disorder, the law that would define the arrow of time. The 19th century had revealed entropy as the law of rising disorder. It declared that heat would not return once dispersed and that every flame eventually sank into stillness. But this new law spoke not only of furnaces and factories, it whispered of time itself. For time always moved in one direction. Memories formed in the past, never in the future. Broken glasses scattered on the floor, never leapt back, whole into the hand. Smoke rose from a flame and diffused into air, but never coalesced, again into a single column. Everyday life was ruled by an arrow, invisible but relentless. Physicists soon gave it a name, the arrow of time. Its origin was tied to the second law of thermodynamics. Entropy always increases, and that increase seemed to mark the forward march of existence itself. Yet a contradiction emerged, one that shook the foundations of science. For the equations of Newton's mechanics, the mathematical heart of motion were perfectly symmetric. They described particles in flight forces in balanced trajectories in space, and they cared nothing for direction. Run them forward, they worked. Run them backward, they worked as well. In the equations, time had no preferred way, but in the world humans inhabit, time is not free to turn. The glass does not unbreak the flame, does not rise, cold heat does not flow from cold to hot. Somewhere between the purity of mathematics and the reality of lived experience, a dissonance had opened, and it demanded explanation. Physicists realized they were staring into a paradox. Entropy defined the flow of time, and yet time seemed to be needed to define entropy, a circle of reasoning that offered no escape. The unease deepened as the 20th century dawned. In 1905, Albert Einstein unveiled the theory of special relativity. It showed that time was not absolute, but woven into the fabric of space itself. Observers moving at different speeds would measure different intervals of time. Clocks ticked more slowly when set into motion, and in 1915, Einstein expanded this vision with general relativity, where gravity was not a force, but the curvature of space-time. These revelations gave rise to a new image of reality, the block universe. In this view, past, present, and future all exist, together as part of a four-dimensional geometry. Time is not flowing, but laid out like a vast landscape already written. A traveler does not make the road already exists. If this was true, then the arrow of time was not a fundamental feature of the universe. It was a property of perception. The laws did not demand a past turning into a future, only the human mind seemed to, but entropy stood stubbornly in the way. If all of space-time was equally real, why did entropy rise in one direction and not the other? Why did the block of the universe contain a low entropy beginning and a high entropy future? Why not the reverse, or a universe where entropy ran down instead of up? The paradox deepened with each attempt at explanation. Some physicists proposed that time's arrow was an illusion, a byproduct of memory. Brains, they argued, are entropy machines, recording only what entropy allows to be recorded. Thus humans perceive a flow because they can remember the past, but never the future. The laws themselves remain untouched, symmetric, and indifferent. Yet this too was unsatisfying, for even if memory is selective, the universe still exhibits a vast gradient of entropy from its silent beginning to its turbulent present. The arrow of time is carved into the structure of stars, galaxies, and black holes, not only into human thought. The mystery grew darker when viewed from the scale of the cosmos. If Newton's equations did not care about direction and Einstein's relativity bound past and future into one timeless geometry, then why was the second law of thermodynamics unyielding in its demand? Why did entropy rise at all? Why not a universe frozen at equilibrium, with no arrow, no change? Boltzmann's statistics offered part of the answer. It was simply more probable for systems to move from order to disorder than the reverse. There were more states available, more ways to be scattered than to be precise. But probability was not law. It was only likelihood. And the staggering improbability of the universe beginning in such a low entropy state only sharpened the question: why should the cosmos have started at the unlikely end of the scale? By the early 20th century, physics had entered a trap of circular reasoning. Entropy seemed to give direction to time, yet time was needed to describe entropy's increase. A concept born in the clatter of engines had now become a philosophical abyss. Einstein himself sensed the depth of the problem. In the block universe, he described time as an illusion of consciousness, but entropy stood like a scar across this illusion. It marked one side of space-time with order and the other with disorder. If the block was timeless, entropy was not. Later, thinkers would struggle with this unease. The physicist Arthur Eddington coined the very phrase "arrow of time," emphasizing that no other feature of physics gave time its direction. Only entropy did. Without it, the universe would be timeless, still symmetrical as equations suggest. With it, time rushed forward with irresistible momentum. The shock was profound, for the second law of thermodynamics was unlike any other law of physics. Newton's equations, Einstein's relativity, Maxwell's electromagnetism, all were reversible. They cared nothing for before and after, but entropy spoke in absolutes. It declared one direction forbidden. The future could not become the past. The past could not be undone. And so physics found itself caught in paradox. Either the universe at its foundation contained a law unlike all others, or the rise of entropy and the arrow of time were illusions born of conditions not yet understood. The debate has never ended. Some see in entropy the only real evidence of time's passage. Others see, in relativity, the proof that time itself is static and that entropy's rise is a statistical artifact. But the contradiction remains unresolved. The arrow of time stands as one of the greatest shocks in the history of science. It forces the question whether time is an objective feature of the cosmos or only a shadow cast by entropy's inevitable climb. It suggests that the silence in which the universe began was not a gentle absence, but a law waiting to be broken. A silence that once disturbed, set into motion the irreversible story of past, present, and future. In the centuries since Clausius first named entropy, and Boltzmann tied it to probability, the mystery has only grown sharper. Entropy rises, but no law demands it should time flows. But the equations refuse to choose a direction. And somewhere between these truths lies the paradox that defines human existence, the shock of the arrow of time. A law both undeniable and inexplicable. A whisper that became a command, the command that tomorrow must always follow today. In the beginning, there was no fire, no roar, no thunderous explosion. There was silence, a silence so deep it defied imagination, a silence written not in sound, but in order. For the birth of the cosmos was not a chaos unleashed, but a perfection balanced. So delicately it seems almost impossible. Modern cosmology calls it the Big Bang, yet this name misleads. It was not an eruption into pre-existing space, not a noise that cracked the void. It was the sudden unfolding of space itself, a universe born from an infinitesimal point, swollen into immensity. And within that swelling there lay a puzzle more profound than the event itself. For the young universe was astonishingly smooth. Its temperature differed by no more than 1 part in 100,000 across the entire sky. Matter and radiation were spread with almost eerie uniformity. The cosmic microwave background, the faint afterglow of that first fireball, bears witness to this stillness. It is a canvas painted in nearly perfect sameness, with only the faintest brushstrokes of fluctuation. From these slight ripples, galaxies would one day rise. But at the beginning, it was quiet, too quiet. To the human mind, the newborn universe might appear turbulent, expanding at furious speed, seething with plasma. Yet beneath this frenzy of motion lay a deep order. Entropy was staggeringly low. By every measure, the universe began not in disorder, but in impossible precision. This silence puzzled one of the most daring minds of modern physics, Roger. Penrose looked at the smoothness of the early cosmos and saw not beauty, but paradox. For if entropy is the measure of disorder, then the beginning of time was improbably ordered. Far more ordered than probability itself would suggest. The odds were so remote they might as well have been zero. And yet here, humanity stands billions of years later, suspended between that improbable origin and the inevitability of future decay. Penrose asked a haunting question. Why did the universe not begin in chaos? Why did it not begin in maximum entropy? Why instead was it balanced on the knife edge of perfection? To answer this, one must look to black holes. These are not merely cosmic monsters, but the ultimate containers of entropy. A single black hole has more entropy than entire galaxies of stars. Entropy is written into the surface area of its event horizon, a discovery that shook physics to its core. The early universe, however, contained no black holes, no collapsed stars, no dense horizons. It was smooth to the point of silence. And so its entropy was lower than at any other moment in history. This creates a tension that science cannot yet resolve. For the laws of probability suggest the opposite. If the universe could have chosen any state, it would almost certainly have chosen chaos. Black holes everywhere, disorder, rampant equilibrium already achieved. But instead, it began in silence. It chose the one path among countless possibilities that allowed time to have an arrow at all here. The mystery sharpens. Entropy rises because it began low. Time flows because order once established must inevitably dissolve. But why did the beginning set such improbable conditions? Why was the stage arranged with such delicate precision? This is not a question answered by thermodynamics alone. It is a question written into the fabric of space-time itself. Penrose proposed the Weyl curvature hypothesis. It suggests that the smoothness of the early universe was not chance but law, that the geometry of space-time forbade the irregularities that would have filled it with disorder. At the beginning, the Weyl curvature, the mathematical expression of tidal distortions in space-time, was exactly zero. No wrinkles, no folds, no hidden chaos, geometry as clean as silence itself. Yet why should the cosmos prefer such a beginning remains a mystery. Physics has no explanation for why entropy was so low at the first moment. It only observes that it was. Telescopes confirm this truth with exquisite precision. The COBE satellite in 1992, the WMAP mission in 2001, and the Planck Observatory in 2013 all gazed into the relic light of creation. They mapped the cosmic microwave background in finer and finer detail. Each mission confirmed the same, haunting smoothness. Tiny fluctuations, yes, seeds of galaxies to come, but beneath them, the same uniformity, the same improbable balance, the silence that underpins everything. The emotional weight of this discovery is profound. It suggests that the entire story of stars and galaxies, of planets and life, of memory and thought, depends on a choice made at the dawn of time. A choice to begin in silence. Had entropy begun high, there would be no arrow of time, no unfolding history. The universe would have been born in heat death already spent. But it was not. It was poised improbably against chaos. And in that improbable balance lay the possibility of everything. Cosmology confronts here not only a scientific puzzle, but a philosophical abyss. If probability cannot explain the low entropy of the beginning, then what can? Was the silence necessary? Was it written into the structure of space-time itself? Or was it a contingency, a chance event? So unlikely it seems almost miraculous, physicists tread carefully around such questions. Science does not speak of miracles, it speaks of laws. Yet the silence at the beginning of time stands as one of the deepest enigmas in all physics, a reminder that the cosmos did not roar into being. It whispered, and that whisper contained the fate of time itself. Even now, as entropy rises, as stars burn and galaxies scatter, the silence of the beginning echoes. It is written in the uniformity of the cosmic background. It is inscribed in the improbable order of the first instant. It is the silence from which every voice of the universe has emerged. And so the story of entropy turns from the clatter of engines and the paradox of equations to the quiet of creation, a quiet so profound that it continues to shape every moment that follows. The universe began too smooth, too perfect, too silent, and in that silence time was given its first breath, its first step, its first arrow. In the late 20th century, humanity built instruments not of bronze or glass, but of orbiting metal and frozen detectors. Eyes launched beyond the distortions of Earth's atmosphere, set adrift to stare into the oldest light the universe still, and carries the cosmic microwave background. The afterglow of creation itself became their target. It was the most ancient whisper, a radiation stretched thin by billions of years of expansion, faint and cold, yet carrying within it the memory of the first silence. The first of these silent witnesses was COBE, the cosmic background explorer launched in 1989. It was tasked with mapping the sky in microwave light, seeking the relic heat of the Big Bang. What it found startled even the most cautious physicists. The radiation filling all of space was not jagged, not uneven, but astonishingly smooth. Its spectrum matched that of a perfect blackbody to an accuracy never before seen in nature. It was the fingerprint of the universe's beginning, clean and uniform, as if reality itself had begun in balance. And yet, beneath this smoothness, COBE discovered something else. Tiny ripples, minute variations in temperature, only 1 part in 100,000 fluctuations. So faint, they were almost invisible. yet they would prove to be the seeds of all future structure. These minute disturbances were the first disorder. From them, galaxies would emerge, stars would ignite, and planets would form. The universe was not perfectly still. It carried in its silence the faint pulse of change. A decade later, WMAP, the Wilkinson Microwave Anisotropy Probe, sharpened the vision. It traced the delicate pattern of fluctuations across the entire sky with unprecedented clarity. The map it produced was like a fossil of the cosmos itself, a frozen image of the universe when it was only 380,000 years old. These variations told of density differences, regions slightly heavier, slightly lighter, destined to collapse under gravity into clusters of galaxies. The first whispers of disorder were revealed not as chaos, but as an elegant pattern, a blueprint for cosmic architecture. Then came Planck, launched in 2009, a satellite of unparalleled sensitivity. It mapped the cosmic microwave background with resolutions so fine that each fluctuation could be traced like a brushstroke in a vast cosmic painting. What Planck confirmed was both exhilarating and unsettling. The early universe was indeed smooth beyond all probability, yet not entirely uniform. The tiny irregularities fit the predictions of inflationary cosmology, a brief exponential expansion that stretched space smooth and amplified quantum fluctuations into cosmic seeds. And yet the paradox sharpened. If inflation smoothed the universe, what smoothed the conditions that allowed inflation to begin? The silence only deepened. Scientists studied the data with awe and unease. For the fluctuations were not random noise, but encoded messages. They revealed the geometry of space, nearly flat on cosmic scales. They revealed the age of the universe, 13.8 billion years, and the proportions of its content, dark matter, dark energy, and ordinary atoms. The ripples were the first footprints of destiny. But they also reminded us that the background, the canvas on which these ripples rested, was improbably uniform. Here lies the paradox that even the most precise satellites cannot resolve entropy should have been high at the beginning. Probability favors disorder, black holes, chaos. Yet what the data reveals is the opposite, an origin of low entropy, an ordered silence from which disorder only gradually rose. The fluctuations prove that the universe was not static. That order was destined to crumble into structure. But the smoothness beneath those ripples insists that the starting point was far more improbable than any theory can comfortably explain. This is the tension that lingers in every map of the cosmic microwave background. Each pixel is a relic of creation, yet the pattern as a whole speaks of a beginning too perfect, as if the universe began in defiance of its own laws, as if entropy itself had chosen silence before motion, order before decay. Physicists describe the paradox in numbers almost beyond comprehension. The probability of such low entropy at the birth of the universe is said to be 1 in 10 to the power of 10 to the power of 120, a number so vast it cannot be imagined. To say it is unlikely is an understatement. It is as though the dice of creation were thrown against infinity and landed on balance. And yet, this is the reality. The data confirms COBE, WMAP, Planck, all instruments of different generations, all gazing into the same ancient light, each found the same truth. The universe did not emerge chaotic. It emerged whisper quiet. What followed? From those whispers was the long story of structure. Gravity took hold of the tiny density differences and amplified them. Galaxies spun from the faintest ripples. Stars ignited in clouds that were once only slightly denser than their surroundings. The first disorder gave rise not to ruin, but to form chaos-seeded beauty. Yet beauty could only arise because the beginning had been so improbably smooth. This is the haunting lesson of the data. The silence of the beginning was not total. It was textured with the faintest imperfections, imperfections that became everything. But the silence itself, the low entropy that allowed an arrow of time to exist, remains unexplained, cosmology thus stands at a threshold. It can measure the fluctuations with exquisite precision. It can trace how they grew into the structures we see today. It can even model the processes by which quantum tremors stretched into galactic seeds. But it cannot tell why the universe began in such improbable stillness. The maps are silent on that question. The relic light carries memory, but not explanation. And so, the paradox endures. The first disorder revealed by satellites was not a collapse into chaos, but the birth of form. The silence of the background remains the greater mystery, a silence that probability rejects. Yet reality affirms. It is here, in the gap between measurement and meaning, that cosmology turns philosophical. Was the silence written into the fabric of space-time itself? Was it the result of hidden laws not yet uncovered? Or was it a singular event, beyond law, beyond probability, beyond reason? The data offers no comfort, only confirmation. The universe began whisper quiet, and from that whisper, time itself unfolded. In the earliest seconds of existence, the universe expanded not gently, but with unimaginable violence. Inflation theory, first proposed in the early 1980s, suggests that in less than a trillionth of a second, space itself ballooned, faster than light could chase its edges. Tiny quantum fluctuations were stretched vast, smoothed across scales far larger than galaxies, ironing out irregularities and leaving behind a cosmos astonishingly uniform. It is a theory both beautiful and terrifying, for it explains why the universe today looks nearly the same in every direction, why the cosmic microwave background is so eerily smooth, and why those faint ripples that do exist carry the pattern that would one day ignite stars. Inflation is often described as the great equalizer, the engine that stretched chaos into calm. And yet, the closer physicists look, the sharper the paradox becomes. Inflation does not truly explain the low entropy of the beginning. It requires it. For inflation to ignite, the initial state of the universe must already have been finely tuned, balanced on a razor's edge of improbability. A condition almost impossibly special had to exist before inflation could even begin to smooth it further. Here lies the heart of the problem. Entropy, the measure of disorder, should by all reasoning have been high at the start. Yet the universe began with entropy staggeringly low, improbably arranged. Inflation does not solve this riddle. It assumes it, pushes it back a step, hiding it behind an exponential veil. Why should the first instant of reality be so unlike all others, so ordered against the tide of probability? The mystery grows more profound when gravity enters the picture. For gravity is not like other forces, where other forms of matter and energy tend to disorder, spreading out evenly. Gravity tends toward clumping, toward collapse. If left alone, gravity produces black holes, and black holes are the densest reservoirs of entropy. Known Roger Penrose, the mathematical physicist, understood this paradox more keenly than most. He proposed what he called the Weyl curvature hypothesis. In it, he argued that the very geometry of spacetime held the key to entropy's secret at the beginning. To understand this is to see that entropy is not merely about the arrangement of particles or the distribution of heat. It is about the shape of spacetime itself. In the presence of matter and gravity, spacetime bends, curves, and twists. The degree of that curvature encodes disorder. Black holes, with their extreme warping of space and time, represent maximum entropy states. Their existence is the embodiment of disorder. Yet the early universe shows no sign of them. The geometry of spacetime at the beginning was astonishingly flat, silent, devoid of the tangled curvature that marks gravitational chaos. This is the silence Penrose spoke of, not silence of sound or light, but silence of geometry. The Weyl curvature, the mathematical measure of gravitational entropy, was near zero at the birth of the cosmos. It was as though the universe had chosen the most improbable page from the book of possibilities, the one where gravity itself lay dormant, waiting in stillness. This stillness defies ordinary understanding, for it is not absence, not emptiness, but a condition more special than any other. To imagine it is to picture an ocean so flat it betrays no ripple, no wind, no current, an ocean not of water, but of space-time itself. From this perfect calm, disorder would one day arise, but in the beginning, silence was written into the very law of existence. And so entropy, the arrow of time, begins not in chaos, but in a profound improbability. The question that lingers is why? Why should the universe begin not in typical disorder, not in the wild tangling of gravitational fields, but in such exceptional stillness? Why would probability, which overwhelmingly favors chaos, permit such an arrangement? Physicists wrestle with this riddle in terms both mathematical and philosophical. Some argue that the question is ill-posed, that perhaps entropy cannot be meaningfully applied to the universe as a whole in its earliest instant. Others suggest multiverse scenarios, where countless universes emerge, and only those rare ones with low entropy beginnings give rise to structure, stars, and observers. But none of these explanations erase the strangeness. They only move the silence further back, displacing the mystery. Without dissolving it, Penrose's vision cuts deeper. If the whale curvature was forced to vanish at the beginning, then the low entropy of the universe is not a statistical accident. It is a law, encoded in geometry. The silence is not chance, but necessity. Yet this raises its own haunting reflection. Why should geometry favor silence? Why should the foundation of reality carry such a rule, one that bends against the flow of probability itself? The paradox escalates when measured against the vastness of possibility. The probability of such a low entropy start is not merely small, it is vanishingly tiny. Penrose once calculated it as 1 part in 10 to the power of 10 to the power of 120, a number so incomprehensibly large that it swallows imagination whole. To say, "It is unlikely" is meaningless. It is beyond unlikely, beyond conceivable odds. Yet here we are, in the universe that exists because of it. This realization turns the mind to philosophy as much as to physics. Was the silence of the beginning a condition demanded by deeper, hidden laws? Was it an echo of something timeless, a geometry older than the universe itself? Or was it singular, a choice without precedent, the one improbable seed from which all existence grew? The satellites that mapped the cosmic microwave background confirmed the smoothness with exquisite precision. The theory of inflation stretched that smoothness across cosmic scales, but neither touched the root of the riddle, the silence of the whale curvature, the geometric stillness at the beginning. Inflation assumes it. Entropy demands explanation of it, and probability denies it. The universe begins in defiance of its own statistics. This is where the mystery escalates into confrontation with infinity itself. For against infinity, the odds of such a beginning vanish. Yet the universe began all the same. It is as though probability is not the deepest law, as though silence, geometry, and time itself rest on foundations beyond calculation. In this tension lies the enduring wonder of cosmology. Every map, every equation, every theory brings us closer to understanding how the first disorder arose, how galaxies formed, how entropy grew. But the first silence remains untouchable, unyielding, resistant to explanation. It is not absence, not emptiness, but a law written in geometry. The universe began not with noise, but with balance, improbable beyond words, yet real beyond doubt. Entropy's story is one of inevitable growth, yet its beginning is a paradox carved against infinity. The silence of the origin is not a void, but a rule, and from that rule, time itself found direction, matter found form, and disorder found its stage. The mystery remains. Why silence? Why order against chaos? Why this improbable beginning in a universe where infinity favors disorder? No theory has yet spoken the final word. The satellites reveal the map. The mathematics describes the curve. The hypotheses explore the shape, but the silence at the origin remains, profound and immovable. It is a silence that does not end, but echoes. A silence that is not emptiness, but foundation. A silence that may be the first and deepest law of reality itself. When science reaches the edge of its maps, speculation becomes not fantasy, but necessity. And at the silence of the universe's beginning, speculation blooms like constellations across the night sky. Each theory rises as a lighthouse, searching for meaning in a sea where probability seems to deny our existence. One vision peers into the vast expanse of the multiverse. If our cosmos is but one bubble in an eternal sea, then silence may not have been a universal law, but a rare condition. Among countless beginnings, some bubbles may ignite in chaos, their entropies high from the start, their structures collapsing before they can host even a whisper of complexity. Others may expand into sterile stillness, never birthing stars, never sculpting galaxies. And among this infinite ensemble, one emerges like a rare chord struck against the noise. The universe we inhabit, where entropy began impossibly low, yet not impossibly forbidden. In this vision, silence was not chosen, but stumbled upon, a chance rarity in an infinite lottery. But the multiverse raises its own paradox, for infinity holds every possibility, and with it comes the danger of explanation by surrender. If all beginnings exist somewhere, then why this one? Why now? Why here? The silence remains, not dissolved, only dispersed into endless mirrors. Others turn to the frontier of quantum cosmology, where the fabric of the universe itself is treated as a wave function. James Hartley and Stephen Hawking proposed the no-boundary condition. In their model, the beginning of time is not a singular point, but a smooth surface, like the rounded pole of the Earth. Before the Big Bang, there is no before. Time curves gently into being, avoiding the singularity's violence. In such a picture, the silence of the beginning is a natural consequence, a quantum state where the universe emerges without edges, without infinite curvature, without the noise of chaos. Here, entropy is not improbably low. It is simply the only way a cosmos could emerge from the quantum haze. Yet, the mathematics of quantum cosmology paints in symbols what the heart struggles to grasp. How can existence arise from a wave function, from probabilities that contain no observer until they collapse into being? The silence is explained, but also transformed into an abstraction, a shape of equations that echo more mystery than certainty. Another speculation imagines the birth of order as the consequence of a false vacuum. Quantum field theory suggests that the vacuum itself, the emptiness between particles, may not be stable. Instead, it may exist in a false state, like a ball resting in a shallow valley, destined one day to tunnel into a deeper one. This tunneling event could spark a universe, a bubble of true vacuum racing outward at near light speed, carrying with it new laws of physics, new constants, and new fields. If our universe began this way, then entropy's silence was the mark of a transition. The calm before expansion was not improbability, but inevitability, a quantum necessity waiting to unfold. In this vision, silence is not chosen. It is the nature of a vacuum teetering on the edge of decay, yet here too lies unease. For false vacuum decay is not only a beginning, it is also a possible end. Even now, physicists calculate that our vacuum may not be truly stable. Far into the cosmic future, or perhaps without warning, the universe could tunnel again, resetting the stage, erasing stars, galaxies, and time itself in a silent flash. Entropy's story would end where it began, in the quantum quiet of a vacuum seeking its truest ground. Other speculations lift their gaze to string theory. where the universe is not confined to the visible dimensions of length, width, height, and time. Instead, it may curl upon hidden geometries, compact dimensions so small they lie forever beyond sight. In the string landscape, there exist billions, perhaps trillions, of possible vacuum states. Each defines a universe with its own physics, its own constants, its own entropic story. Some of these hidden landscapes may favor low entropy beginnings, where silence is encoded in geometry we cannot see. The improbability of our universe becomes less startling if it is one selection among a cosmic library whose shelves stretch beyond imagination. But string theory, too, suffers the weight of its abundance. If everything is possible, what is explanation? The silence of the beginning may be buried in landscapes too vast for reason to ever traverse. And then there is Roger Penrose, returning once more with a vision that stretches beyond even infinity. His conformal cyclic cosmology proposes that the universe is not a one-time event, but an endless cycle. Each cosmic epoch ends in vast entropy, with black holes evaporating and matter dissolving into radiation. Over inconceivable spans of time, the universe empties into near-perfect uniformity. At that point, with all scale erased, the geometry of the cosmos can be reinterpreted as the beginning of a new Big Bang. The end becomes the beginning, entropy resets, and silence is reborn. In this vision, the improbable order of our universe is not improbable at all. It is the necessary rebirth of eternity's rhythm. To contemplate this cycle is to see silence not as a singular miracle, but as a pulse, beating across the infinite ages of time. Each silence carries forward the memory of entropy's exhaustion, transforming death into birth, collapse into expansion. Entropy is not opposed to silence. It is the very reason silence can begin again. Each of these theories, multiverse, quantum cosmology, false vacuum decay, string landscapes, conformal cycles, stands as a monument of human thought. Each one bends the mind toward possibilities that stretch language, mathematics, and imagination to their limits. And yet, each one, in its own way, circles the same haunting truth. The silence of the beginning remains untouchable. The multiverse suggests we are rare. Quantum cosmology suggests we are inevitable. The false vacuum suggests we are temporary. String theory suggests we are one note in a vast symphony. Penrose's cycles suggest we are eternal. But none can erase the awe of the fact itself. That entropy began not in chaos, but in quiet, not in noise, but in balance. What does it mean that silence was chosen at the beginning of time? Was it the mark of deeper laws, unseen and eternal? Was it the echo of infinity, narrowing into a single possibility? Or was it perhaps the only way for time itself to be born? These speculations do not close the mystery, they deepen it. For every explanation widens the horizon, and the silence at the origin remains like a horizon itself, always retreating, always just beyond reach. The story of entropy is the story of time, and the story of time is the story of silence breaking into sound, of stillness flowering into motion. At the heart of that story is the most improbable of beginnings, a universe that began against infinity, in silence. The silence of the beginning is not a relic of philosophy alone. It is a question now whispered through instruments stretched across the earth and stationed in the deep night of space. Each one is an ear pressed to the cosmos, listening for echoes of the improbable calm that marked the universe's first breath. The James Webb Space Telescope, suspended 1 million miles from Earth, peers further back than any eye has before its mirrors, polished to atomic precision, open a window onto the infancy of galaxies. What it seeks is not merely beauty, but evidence. Light stretched across more than 13 billion years, carrying the record of how structure first arose from smoothness. If inflation is true, the galaxy's web finds should cluster in patterns seeded by quantum fluctuations, ripples frozen into the fabric of space during that brief, violent expansion. The telescope's silence is not passive. It is filled with faint photons, each one a messenger from a time when entropy had barely begun to stir. And in those patterns, scientists hope to glimpse whether inflation was a true sculptor of order, or only a story written to hide a deeper law on Earth. In colossal rings buried beneath the soil, particle accelerators probe another frontier. The quantum fields that may have governed the universe's first silence. The Large Hadron Collider at CERN has already revealed the Higgs boson, a particle tied to the field that grants mass to all matter. Yet the Higgs also holds a darker secret. Its measured mass suggests that our universe may rest in a precarious metastable state. The vacuum of space could be false, a shallow valley destined one day to decay into a deeper state, collapsing everything in an instant. If this is true, then the silence of the beginning may have been born not of balance but of fragility, the tremor of a field resting on the edge, of catastrophe. Accelerators now collide protons at energies never before achieved, searching for signs that the Higgs is not alone, that hidden particles or forces stabilize our vacuum and preserve the fragile silence above mountains and beneath oceans. Gravitational wave observatories listen to space-time itself. When two black holes collide, they ripple the fabric of the universe, ringing like cosmic bells. But physicists dream of something older, an echo not of stars or galaxies, but of inflation itself. If inflation occurred, it would have left behind gravitational waves imprinted on the very radiation of the cosmos detectors like LIGO and Virgo, and projects on the horizon such as LISA seek these primordial signals, vibrations from the first trillionth of a second. To capture such a wave would be to hold a fragment of the silence breaking, a direct fingerprint of how the first disorder was born in vast rooms filled with whirring processors. Supercomputers now take up the story. They model entire universes in digital form, seeding them with initial conditions and watching entropy grow across billions of simulated years. These simulations reveal how galaxies swirl into clusters, how dark matter weaves its invisible web, how entropy rises with the birth of black holes. But when cosmologists rewind the models to the beginning, they confront again the same improbability. The probability of a universe beginning as smooth as ours appears vanishingly small. And so, they run the simulations again, probing whether some hidden law might force the silence, or whether our cosmos truly stands as a statistical outlier among infinite possibilities. Even in the quiet of Antarctic ice, instruments listen for whispers. Experiments like IceCube bury detectors beneath a kilometer of frozen clarity, capturing neutrinos, ghostly particles that barely interact with matter. Some of these may carry traces of the earliest processes, born in the silence before stars elsewhere. In high deserts, radio arrays search for the faint hydrogen glow of the first atoms, listening for the moment when darkness gave way to light. The pursuit of entropy's origin is thus not confined to a single tool or a single theory. It unfolds as a symphony, each instrument tuned to a different frequency of reality. The Webb telescope watches the first galaxies ignite. Particle accelerators unravel the vacuum. Gravitational wave detectors strain. For echoes of inflation, supercomputers conjure statistical shadows of beginnings. Together, they form a network of eyes and ears, all bent toward one question. Why did silence prevail when probability demanded noise? And yet, for all their precision, the answer remains elusive. Each measurement narrows the field, each discovery draws the net tighter, but the silence remains hidden, like a horizon always receding. The cosmos gives up fragments of its story, never the whole. Every telescope reveals the light of stars, but not the quiet geometry that preceded them. Every collider smashes matter into shards, but not the rule that steadied the first vacuum. Every simulation runs countless beginnings, yet the improbable balance of our own remains unmatched. This is the paradox of modern science. The closer humanity looks, the clearer the silence becomes, and the deeper its mystery grows. For what these instruments reveal is not chaos, but coherence, not disorder, but patterns so subtle they seem guided. And in these patterns lies the same truth that haunted Clausius, Boltzmann, Penrose, and Hawking. The universe did not begin in chaos, but in a silence so perfect it defies the odds of infinity. Perhaps, one day, Webb will glimpse galaxies too smooth or too rough, forcing inflation to be rewritten. Perhaps accelerators will uncover new fields that anchor the vacuum, making silence necessary. Perhaps gravitational waves will carry echoes of the first expansion, proving that silence was stretched across eternity in a single violent breath. Or perhaps no instrument will ever pierce the veil. Perhaps the silence is not hidden in the data, but in the laws themselves, forever beyond reach, yet the search does not relent. Because silence is not absence, it is presence. It is the one fact that underpins all others. Every detector, every telescope, every supercomputer runs not to escape the mystery, but to deepen it, to bring humanity nearer to the horizon of understanding. And so, the silence of the beginning is still under investigation. It flows through the mirrors of Webb, the magnets of CERN, the interferometers of LIGO, and the circuits of supercomputers. It waits in the sky, in the vacuum, in the faint gravitational tremors of space-time. It remains, even now, not explained but whispered, a secret carried in the background of all things, patient, immovable, and unresolved. The universe is often described as a machine of inevitability, where time moves forward because entropy demands it. Disorder rises, stars burn out, galaxies drift apart, and heat spreads thin across the canvas of space. Yet at its very beginning, the cosmos was not chaos. It was silence, a silence so unlikely, so improbable, that it defies the arithmetic of chance. If entropy is destiny, then why was order chosen first? Why did the universe begin in a state of such extraordinary calm? This is the paradox that haunts the science of origins. The equations of physics can describe the unfolding of events once the initial stage is set. But the reason the curtain rose upon silence rather than upon chaos remains an unanswered question. Some see this silence as a prelude, a deliberate pause before the storm of time. Others view it as illusion, born from perspective. For two, live within time is to see its arrow only in one direction, from smoothness to disorder, from memory to forgetfulness. Perhaps the silence was not silence at all, but simply the way the universe appears when viewed from inside the river of entropy. Time itself may be nothing more than the measure of entropy's rise. Without it, there is no before, no after, no sequence. Entropy is the memory of the cosmos. It is what separates the newborn fire of stars from their eventual ashes. It is what allows galaxies to tell stories through the light of their spirals. And it is what allows minds, here on Earth, to remember yesterday and anticipate tomorrow. If the cosmos had not begun in silence, if it had emerged chaotic and saturated with entropy, time might never have flowed. There would have been no gradient, no direction, no unfolding. All possibilities would have existed at once, without a past or a future to distinguish them. Silence, improbable though it was, may be the reason time exists at all. This reflection draws the mind toward deeper questions, where physics approaches the boundaries of philosophy. Was the silence a law, written in the geometry of space-time? Or was it an accident, one universe among countless failed attempts where chaos drowned possibility before it could breathe? Theories stretch to grasp this enigma. Some imagine a multiverse, where countless beginnings bloom and collapse, each with different entropies, different arrows of time. In such a landscape, silence might be rare, but inevitable somewhere. And it was here, in this universe, that the seed was sown. Others, like Penrose, imagine cycles of creation, where the death of one universe resets the stage for the next, entropy erased by eternity itself. In such visions, silence is not chosen once, but again and again woven into the rhythm of existence. Yet the truth remains hidden. Every telescope, every detector, every theory that reaches for the silence can only circle its edge. The silence itself does not speak. It only echoes through background radiation, through the laws of thermodynamics, through the way galaxies coalesce and decay. Perhaps the question itself bends under its own weight. To ask why entropy began low is to assume that beginnings are anchored in reason. Yet the cosmos is not obliged to satisfy reason. It unfolds whether or not it answers. Still, there is a quiet resonance in wondering. For humans, bound to the arrow of time, the silence is not abstract. It is intimate. It is the reason memory exists, the reason stories can be told, the reason there is a past to reflect upon and a future to imagine. Without silence, there would be no history, no evolution, no awareness. Life itself is a delicate flame burning against the rise of entropy, made possible only because the cosmos began improbably ordered. The silence was not absence. It was potential. It was a law not written in words, but in geometry, in the smoothness of space-time, in the near-perfect balance that allowed matter to gather, stars to ignite, and eyes to open beneath their light. The silence was a stage on which everything could play out, and so the universe continues, entropy rising, silence fading into distance. Yet the question remains, suspended like a note that never resolves. Was silence chosen, or was it inevitable? Was it the only path the cosmos could take, or one among infinite, unrealized possibilities? Perhaps the answer lies not in why silence gave birth to entropy, but in recognizing that it did. That against probability, against the weight of chance, order came first, and from it, time. From it, memory. From it, every star and every thought. The mystery binds science to philosophy and humanity to the eternal unfolding of time. For to live within the universe is to be a child of its silence, carried forward by its entropy, always asking, always wondering, as the cosmos expands into the unknown. The silence is not gone. It lingers still in the faint afterglow of the cosmic microwave background, in the equations of relativity, in the improbable fact that order once reigned. It whispers through telescopes and detectors, through theories and speculations, reminding all who listen that the greatest mystery of the universe may not be how it ends, but how it began. And so the reflection closes not with an answer, but with a question that outlives the stars. Why did silence give birth to entropy? Why did order rise before chaos? The universe does not say. It only unfolds, page by page, in the book that silence once opened. In the beginning, there was silence, not the silence of emptiness, but of perfection, a balance so precise that it allowed space and time themselves to awaken. From that silence came the first fluctuations, the trembling seeds of galaxies. From those galaxies came stars, and from stars, the elements of life. Entropy has risen ever since, a tide that cannot be stopped, carrying the universe toward a fate of cold dispersal. Yet this tide was only possible because the waters were once still. The improbable calm of the beginning is the secret that underlies every heartbeat, every memory, every question. Scientists have measured it in radiation, modeled it in equations, and dreamed of its origin through theories of inflation, multiverses, and cyclic time. Yet none have broken through the silence itself. The paradox endures. The universe began not in chaos, but in improbable order. Perhaps the silence is not meant to be solved, only witnessed. A reminder that existence rests upon mystery, and that the human mind, small though it is able to hear its echo. In the glow of distant galaxies, in the faint hiss of the cosmic microwave, background in the laws of thermodynamics and the arrow of time, the silence still whispers. It whispers that order preceded chaos, that time flows only because of it, and that everything we know is bound to its improbable gift. The cosmos does not answer why, it simply unfolds, and as it unfolds, humanity looks upward, carried forward by entropy, yet forever haunted by the silence that made beginnings possible. The final question remains, not why the universe will end in disorder, but why it began in silence.